A multiplexer is a digital switch designed to route data from multiple input sources into a single, unified output stream. This routing capability originates at the physical layer, specifically within CMOS transmission gates. These components are built using paired P-channel and N-channel transistors to create a controlled pathway for electrical signals. When the control signal, S, is 0, the top transmission gate activates. Data input D0 flows directly to output Y. Flip to 1, the top gate closes and the bottom turns on, routing data D1 to the output instead.
We can write this physical switching behavior as a Boolean equation. Output Y equals S0 and input 0, or S and input 1.
Engineers summarize this binary routing behavior using functional and logical truth tables, which map every possible control state to its resulting output.
Adding a second control variable expands this logic into a 4-to-1 multiplexer. Two select lines provide 4 unique binary combinations, creating 4 distinct input pathways. Multiplexers can also solve complex 3-variable and 4-variable logic equations directly. By creatively wiring the inputs, engineers rely on the multiplexer as a universal logic gate, replacing dozens of individual and, or, and not gates to save critical space on a circuit board. We are going to look at exactly how to construct this programmable foundation, adapting a basic data router into a tool capable of computing advanced logical functions.
Scale from 2 inputs to 4, the architecture requires 2 control variables. This expansion allows the system to distinguish between 4 separate data sources. 2 control variables provide 4 unique binary combinations. Each combination enables a specific logical pathway through the circuit, representing one of the 4 minterms in the 4-to-1 equation. Scaling further to an 8-to-1 multiplexer requires 3 control variables, which generate 8 unique combinations to select from 8 data inputs. Multiplexers are not limited to routing data. By holding data inputs at fixed values and using variables as the control signals, they can implement general-purpose logic. Consider a logic function defined by minterms 1, 2, 6, and 7. We can execute this specific function without using a custom array of individual logic gates. Here, the target function's truth table output maps exactly to the data pins of an 8-to-1 multiplexer. We map the 3 variables, A, B, and C, directly to the control lines. The data inputs are hardwired to constant 0s and 1s, matching the function's output. This turns the multiplexer into a hardware-based lookup table, allowing immediate implementation of any Boolean function. While an 8-to-1 multiplexer is effective, we can reduce the hardware footprint by fitting that same function onto a smaller 4-to-1 multiplexer. This requires a technique called variable folding, where we use only n-1 variables for the control inputs. For our function, A and B act as control signals, while the third variable, C, is mapped directly into the data inputs. Segmenting the truth table into pairs based on A and B reveals the relationship between C and the output. Where A and B are 0, F equals C. The remaining pairs yield C', 0, and 1, providing the 4 multiplexer inputs. By tying inputs to dynamic variables instead of static constants, engineers can implement logic functions using significantly less hardware. When functions reach 4 variables, dimensionality reduction becomes a necessity. Consider this complex Boolean function, requiring inputs A, B, C, and D. If we are restricted to a 4-to-1 multiplexer, we must find a way to implement 4-variable logic using only 2 control lines. This constraint forces us to fold 2 variables into the data inputs simultaneously. To begin, we identify the 2 most frequent variables in the equation, in this case B and C, and assign them as our control signals. Using Boolean algebraic factoring, we can rewrite the function to isolate the terms relative to our control variables, B and C. The resulting expression reveals the 4 specific signals required for the multiplexer's data ports, 0, D', A, and 1. Although algebraic factoring works, it is time-intensive and prone to error when dealing with high-complexity functions. The truth table reorganization method offers a more robust visual alternative to manual Boolean algebra. We start with a standard truth table for 4 variables, accounting for all 16 possible binary states. The first step is to reorganize the columns so the chosen control variables, B and C, are grouped together. In this reorganized table, the rows are partitioned into 4 distinct blocks based on the constant states of B and C. In the first block, where B and C are 0, the output S remains a constant 0. Within the second block, where B is 0 and C is 1, the output F is the exact inverse of variable D. In the third block, with B at 1 and C at 0, the output matches variable A. In the final block, where both B and C are 1, the output is held at a constant 1. These four visually derived expressions, 0, D', A, and 1, are then assigned to the four data ports of the multiplexer. By utilizing this systematic visual compression, engineers can replace sprawling logic gate arrays with a single multiplexer, transforming a simple routing switch into a dense, highly optimized logic implementation.
Thanks for watching. See you next time.